Far beyond the warmth of the inner solar system, where sunlight grows thin and temperatures drop toward extremes, a giant world dominates the darkness. Jupiter hangs in the black emptiness of space, its banded clouds swirling in patterns that have persisted for centuries, perhaps longer. Around this massive planet, 95 moons trace their paths through the void, each one a world with its own character and story. Tonight, we travel outward to explore every strange world in this remarkable system, beginning with the most violent moon in the entire solar system. The innermost of the 4 large moons orbits so close to Jupiter that the giant planet fills nearly 20 degrees of its sky. From the surface of this moon, Jupiter would appear roughly 40 times larger than our moon appears from Earth, an overwhelming presence always visible overhead. This world is called Io, and it looks like nothing else we have ever found in our exploration of the cosmos. The surface stretches out in shades of yellow, orange, red, and black, resembling something between a pizza and a painting left too long in the sun. You are listening to the Drowsy Astronaut, and tonight we begin a slow, unhurried journey through Jupiter's collection of moons. There is no rush in what follows, no test to pass, no information you need to remember by morning. We will simply move through this distant corner of the solar system together, exploring each world at a gentle pace. If you enjoy this journey, consider leaving a comment about where you are listening from tonight, and perhaps a like or subscription if the channel has helped you rest. The colors covering Io's surface come from sulfur in its many forms, deposited across the landscape by constant volcanic activity. Sulfur changes color depending on its temperature and molecular structure, creating the palette that makes Io so visually striking. Fresh volcanic deposits often appear bright yellow or orange, while older material darkens to deep reds and browns over time. Black patches scattered across the surface mark the hottest lava flows where temperatures have exceeded what sulfur can withstand, leaving behind silicate rock exposed directly. Io is the most volcanically active body we have ever discovered, with over 400 active volcanoes identified across its surface. To understand this number, consider that Earth has perhaps 50 volcanoes that erupt in any given year, and we consider our planet quite geologically active. Io produces so much volcanic material that its entire surface is replaced over geologically short timescales, perhaps every million years or so. Craters from asteroid impacts, which cover most ancient surfaces in the solar system, are almost entirely absent here, because lava flows bury them before they can accumulate. The volcanoes on Io do not look quite like the volcanoes we know on Earth, at least not all of them. Many of the most prominent features are calderas, which are collapsed structures rather than the built-up cones we might picture when thinking of a volcano. These calderas form when the ground above an underground magma chamber drops inward after an eruption empties the chamber below. Some of these depressions stretch dozens of kilometers across, dark floors surrounded by brightly colored deposits that spray outward during eruptions. One of the most famous volcanic features on Io carries the name Pele, after the Hawaiian goddess of fire and volcanoes. Pele produces enormous plumes that can rise 300 kilometers above the surface, spraying sulfur dioxide into the near vacuum above the moon. The deposits surrounding Pele form a distinctive red ring, visible from orbit, created by a particular form of sulfur that condenses at certain temperatures. This ring extends outward for hundreds of kilometers in all directions, a signature visible in images taken by every spacecraft that has visited the Jupiter system. Another volcanic feature, called Loki Patera, holds the distinction of being the most powerful volcano in the entire solar system. Loki is a dark caldera roughly 200 kilometers across, containing what appears to be a lake of cooling lava covered by a thin crust. Periodically, this crust overturns in a process that takes months to complete, releasing tremendous amounts of heat, detectable even from Earth-based telescopes. The energy output from Loki alone exceeds the total volcanic output of all volcanoes on Earth combined, a single feature outproducing our entire planet. Prometheus is another volcano that has remained persistently active throughout the decades we have observed Io up close. When the Voyager spacecraft flew past in 1979, Prometheus was erupting, and when Galileo arrived 16 years later, it was still going. The volcanic plume from Prometheus reaches about 100 kilometers high, constantly replenishing a bright ring of sulfur dioxide frost around the vent. Scientists have watched the lava flows from Prometheus advance across the surface over time, consuming older terrain as the eruption continues without pause. The lava flowing across Io's surface travels in rivers that can extend for hundreds of kilometers before cooling and solidifying. Some flows appear to cascade over cliffs and into calderas, creating scenes that would be spectacular beyond imagination if any human eyes could witness them. The temperature of the lava often exceeds 1,500 degrees Celsius, hot enough to glow brilliantly even in the vacuum of space. These are among the hottest surface temperatures measured anywhere in the outer solar system, creating pools and rivers of liquid rock on a moon that orbits far from the sun. Despite the intense volcanic activity, Io also possesses mountains that rank among the tallest in the solar system. Boissaule Montes rises approximately 17 kilometers above the surrounding terrain, taller than any peak on Earth measured from base to summit. These mountains do not form from volcanic building like shield volcanoes on Earth or Mars would. Instead, they arise from compression in Io's crust, pushed upward as the constant volcanic activity shifts material around beneath the surface. The process that creates these mountains involves the crust being squeezed and buckled as vast amounts of material erupt in one area and accumulate in another. Over millions of years, this shifting produces tilted blocks of rock that jut upward at sharp angles, their slopes too steep for volcanic material to cling. The mountains often appear isolated, surrounded by the colorful plains of sulfur deposits, looking almost out of place amid the otherwise flat, volcanic landscape. Some mountains show evidence of massive landslides on their flanks, where slopes grew too steep to remain stable. Io's thin atmosphere consists almost entirely of sulfur dioxide, the same gas released by its countless volcanoes. This atmosphere is constantly being replenished from below and stripped away from above, making it one of the most dynamic atmospheres in the solar system. On the day side of Io, sublimation from volcanic frost adds material to the atmosphere, puffing it up slightly compared to the night side. Jupiter's intense radiation environment continuously knocks particles away, sending them into a torus of charged material that follows Io's orbit around Jupiter. The atmospheric pressure at Io's surface is incredibly low, less than 1/1000th of the atmospheric pressure at sea level on Earth. An astronaut standing on Io would find the atmosphere essentially indistinguishable from a hard vacuum, providing no protection from radiation or micrometeoroids. Sound would not travel through this thin envelope of gas, meaning the volcanic eruptions happen in complete silence from any observer's perspective. Plumes rise and fall, lava flows and cools, mountains crumble, all without a whisper to mark these events. Standing on Io's surface, an observer would see Jupiter dominating the sky, its bands of orange and white clearly visible even without magnification. The ground beneath would be a complex tapestry of colors, from bright yellow plains to dark calderas steaming with heat that shimmers visibly against the cold black sky. In the distance, a volcanic plume might rise in an elegant curve, particles following ballistic arcs in the low gravity before falling back to the surface. The silence would be absolute, broken only by vibrations transmitted through the ground beneath your feet from the churning interior. The reason Io experiences such extreme volcanic activity lies in its relationship with Jupiter and its neighboring moons. Jupiter's enormous gravity reaches across the relatively small distance to Io and pulls on the moon with tremendous force. This pull is slightly stronger on the side of Io closest to Jupiter than on the far side, creating what scientists call tidal forces. Additionally, the other large moons, Europa and Ganymede, pull on Io as well, keeping its orbit slightly elliptical rather than perfectly circular. This elliptical orbit means that Io's distance from Jupiter changes slightly during each 42-hour trip around the planet. As the distance changes, the strength of Jupiter's tidal pull also changes, causing Io to flex slightly, like a rubber ball being repeatedly squeezed. This constant flexing generates friction inside the moon, and that friction produces heat, enormous amounts of heat that must escape somehow. The escape route for this energy is volcanic eruptions, driving the spectacular activity we observe across Io's tormented surface. The amount of heat flowing out of Io exceeds 100 trillion watts, more than twice the internal heat output of our entire planet Earth. This energy comes not from radioactive decay, as most planetary heat does, but from the gravitational interaction with Jupiter and the other moons. Io has been experiencing this heating for billions of years, and the volcanic activity has likely persisted throughout most of that time. The moon has essentially turned itself inside out many times over, with material cycling from interior to surface and back again through the eons. Io completes an orbit around Jupiter in just 1.77 Earth days, or approximately 42.5 hours. During each orbit, the moon experiences a complete cycle of being stretched and compressed by Jupiter's varying gravitational pull. The surface of Io rises and falls by roughly 100 meters during this cycle, a remarkable amount of flexing for a solid world. Earth's tides, by comparison, cause our solid ground to rise and fall by only about 30 centimeters at most. The relationship between Io, Europa, and Ganymede forms what astronomers call an orbital resonance, a synchronized dance of gravitational interaction. For every single orbit that Ganymede completes around Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4. This 4 to 2 to 1 relationship has been stable for an extraordinarily long time, perhaps billions of years. The resonance prevents any of these moons from settling into perfectly circular orbits, which would reduce the tidal flexing and allow them to cool. As our attention lingers on Io's volcanic plains and towering mountains, the heat and constant transformation make this world feel alive in a way few places are. Every eruption reshapes the surface. Every lava flow buries the evidence of what came before. Every plume sends material into space to form the torus of charged particles surrounding Jupiter. Io is a world of fire orbiting a cold giant, kept warm by the invisible hand of gravity reaching across the emptiness between worlds. And yet, just beyond Io, orbiting only a little farther from Jupiter, lies a moon of a completely different character, a world of ice that may hide something remarkable beneath its frozen shell. The contrast between neighboring worlds could hardly be more striking than the difference between Io and the moon that orbits just beyond it. Where Io blazes with volcanic heat and churns with constant activity, Europa presents a face of icy calm, a smooth white sphere reflecting sunlight with unusual brightness. This world measures only slightly smaller than Earth's moon, yet it has captured the attention of scientists more than almost any other object in the outer solar system. Europa's appeal lies not in what we can see on the surface, but in what almost certainly exists below the ice. Europa's surface is remarkably smooth on a global scale, lacking the tall mountains, deep canyons, or massive impact craters that characterize most solid bodies in the solar system. The ice shell stretches out in all directions from any vantage point, broken only by a complex network of dark lines that crisscross the landscape. From orbit, these lines give Europa the appearance of a cracked egg, the fractures following curved and intersecting paths that seem almost chaotic. The relative flatness of the surface tells us something important. This ice is young, geologically speaking, which means something is erasing the ancient record. Impact craters accumulate on solid surfaces throughout the solar system, building up over millions and billions of years as asteroids and comets strike worlds without atmospheres to burn them up. The near absence of impact craters on Europa suggests that the surface we see today is only 10 to 30 million years old at most. Something is resurfacing this moon, covering over the ancient craters before they can accumulate to the densities we see on other icy worlds. The most compelling explanation is that the ice shell is active, with material from below rising up and freezing to form new surface layers. The dark reddish-brown lines crossing Europa's surface are called lineae, a Latin word simply meaning lines, and they hold important clues about what is happening beneath the ice. Some of these features stretch for thousands of kilometers across the moon's surface, cutting through older terrain in ways that reveal their relative ages. The lines form when the ice shell cracks under stress, allowing material from below to well up and fill the gap before freezing in place. The reddish-brown color may come from salts carried up from a liquid water ocean beneath the ice, minerals that had been dissolved in the water for countless years. Close examination of Europa's lineae reveals that they often appear in pairs, two parallel ridges with a valley running between them. The formation process involves the ice shell cracking and then being pulled apart slightly by tidal forces, with warmer ice rising up to fill the gap. As this warmer material freezes, it forms the ridges on either side of the original crack, creating the paired structure we observe. Over time, newer cracks cut across older ones, creating the complex, cross-hatched pattern visible from orbit. Some regions of Europa display what scientists call chaos terrain, where the normal pattern of ridges and plains gives way to something that looks like jumbled ice blocks, refrozen in place. These regions appear as if the surface ice shattered into pieces that drifted and rotated before freezing back together in a new configuration. The individual blocks in chaos terrain can often be fitted back together like puzzle pieces, revealing how far they moved before refreezing occurred. This behavior strongly suggests the presence of liquid water, or at least slushy ice beneath the surface, allowing the blocks to float and drift. The most famous region of chaos terrain on Europa is called Connemara Chaos, named after a region in Ireland known for its rocky, fragmented landscape. In Connemara Chaos, ice blocks the size of small cities appear to have broken apart and shifted positions before freezing in their current arrangement. Some blocks have rotated significantly from their original orientations, while others have tilted at angles that reveal their broken edges. The matrix material between the blocks appears darker and smoother, likely representing material that welled up from below and refroze around the displaced ice. The evidence for a liquid water ocean beneath Europa's ice shell comes from multiple independent lines of observation and analysis. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, measured Europa's magnetic field and found something remarkable. Europa generates no magnetic field of its own, but the spacecraft detected a field that changed in response to Jupiter's rotating magnetic field. This induced magnetic field can only exist if Europa contains a layer of electrically conductive material, and the most likely candidate is a global ocean of salty water. Further support for the ocean comes from measurements of Europa's surface response to Jupiter's gravitational pull. As Europa orbits, Jupiter's tidal forces cause the Moon to flex slightly, and the amount of flexing depends on what the interior is made of. If Europa were solid ice and rock all the way through, the surface would flex by only about a meter during each orbit. But measurements suggest the surface actually flexes by about 30 meters, a much larger amount that implies a liquid layer decoupling the ice shell from the rocky interior. The ocean beneath Europa's ice is believed to contain roughly twice as much water as all of Earth's oceans combined, despite the Moon being smaller than our planet. Scientists estimate the ocean depth at perhaps 60 to 150 kilometers, far deeper than any ocean on Earth. The pressure at the bottom of this ocean would be tremendous, roughly corresponding to the pressure many kilometers beneath Earth's ocean surface. What conditions exist at this ocean floor remains one of the most compelling questions in planetary science today. The ice shell covering Europa's ocean varies in estimated thickness, depending on the study and method used, with figures ranging from a few kilometers to over 30 kilometers. A thinner ice shell would mean more direct communication between the ocean and the surface, with material moving more easily between the two. A thicker shell would provide more insulation, but would also make the chaos terrain harder to explain, without invoking some additional process. Current best estimates suggest the ice is probably 10 to 25 kilometers thick, substantial, but not impenetrable. The ocean beneath the ice almost certainly remains liquid because of the same tidal heating process that drives Io's volcanism, though to a lesser degree. Europa's orbit is kept slightly elliptical by its resonance with Io and Ganymede, causing regular flexing that generates internal heat. This heat is not enough to melt rock and produce volcanoes as on Io, but it appears sufficient to maintain liquid water beneath the insulating ice shell. The ocean may have existed in liquid form for billions of years, continuously warmed by this gravitational interaction. What makes Europa's oceans so scientifically interesting is the possibility that conditions might be suitable for life to develop and persist. On Earth, life thrives wherever liquid water exists, from hot springs to the deepest ocean trenches to aquifers buried deep underground. Europa offers liquid water that may have been stable for billions of years, along with potential energy sources and chemical nutrients. The rocky sea floor may host hydrothermal vents, similar to those that support ecosystems in Earth's deep ocean trenches. Hydrothermal vents on Earth occur where water seeps into cracks in the ocean floor, is heated by volcanic activity below, and rises back up, carrying dissolved minerals. These vents support entire ecosystems that live independently of sunlight, drawing energy instead from chemical reactions involving the minerals in the vent fluids. If Europa's rocky interior is geologically active, similar vents could exist at the bottom of its dark ocean, providing both heat and chemical energy. The combination of water, energy, and nutrients represents the basic requirements for life as we understand it. The surface temperature on Europa averages around -160 degrees Celsius, far too cold for liquid water to exist without protection. The ice shell acts as an insulating blanket, trapping the heat generated by tidal flexing within the interior below. Direct sunlight plays almost no role in warming this ocean. The heat comes entirely from gravitational interactions with Jupiter. This means Europa's ocean exists in permanent darkness, illuminated only by whatever faint bioluminescence might evolve if life developed there. The surface ice itself is primarily water ice, but spectroscopic observations have detected the presence of other materials mixed in. Sulfuric acid appears to be present in some regions, possibly created when sulfur from Io's volcanic emissions is implanted into Europa's ice by Jupiter's radiation. Salts, including magnesium sulfate and possibly sodium chloride, have also been detected, likely originating from the ocean below. These salt deposits appear concentrated in the darker regions of the surface, supporting the idea that material from the ocean occasionally reaches the surface. Scientists have proposed that water from the ocean might occasionally escape through the ice shell to reach the surface in the form of plumes. In 2012, and again in 2014, observations from the Hubble Space Telescope hinted at possible water vapor plumes erupting from Europa's surface. These observations remain somewhat controversial, as the signals were near the limits of what Hubble could detect, but if confirmed, they would provide a way to sample ocean material without drilling through the ice. Future spacecraft may be able to fly through such plumes and directly analyze what the ocean contains. The radiation environment at Europa is extremely harsh, making the surface one of the most inhospitable places in the solar system for anything alive. Jupiter's magnetic field traps charged particles that bombard Europa continuously, delivering a radiation dose lethal to most Earth organisms within days or less. Any life that might exist on Europa would need to remain protected beneath the ice, shielded from this constant bombardment. The ice shell that separates the ocean from space also separates any potential biosphere from the harsh conditions above. Looking across Europa's fractured surface, the scene is one of quiet activity, happening slowly over geological timescales. The ice cracks and shifts, material wells up from below, new terrain forms, while old terrain is buried or broken apart. Somewhere beneath this frozen landscape, a dark ocean may lap against shores of ice, warmed by the invisible pull of Jupiter's gravity. Whether anything swims in those lightless waters remains one of the great, unanswered questions of our time. A mystery that draws our attention and our spacecraft to this distant, frozen world. Beyond Europa, orbiting still farther from Jupiter, lies a moon larger than any other in the solar system, a world that surpasses even the planet Mercury in size. Ganymede holds secrets of its own, including evidence for yet another ocean hidden beneath ice, and a magnetic field unlike any other moon possesses. Our journey continues outward to explore this giant among moons and the features that make it unique. The moon that orbits beyond Europa holds a distinction that no other moon in the solar system can claim. It is the largest of them all. Ganymede measures 5,268 kilometers across, exceeding the diameter of the planet Mercury by nearly 400 kilometers. If Ganymede orbited the Sun instead of Jupiter, we would almost certainly classify it as a planet, complete with its own atmosphere and magnetic field. Instead, this giant world traces its path around Jupiter every 7 Earth days, the third of the 4 large moons in order of distance. Approaching Ganymede from space, the surface presents a mottled appearance quite different from either Io's volcanic palette or Europa's clean white ice. 2 distinct types of terrain cover the surface, and the boundary between them is often sharp enough to see clearly from orbit. Dark regions appear ancient and heavily cratered, representing some of the oldest surfaces we have found anywhere in the outer solar system. Lighter regions display grooved terrain with parallel ridges and valleys that suggest a more complex geological history. The dark terrain on Ganymede covers roughly 1/3 of the surface and bears the scars of billions of years of bombardment. Impact craters crowd together in these regions, overlapping one another in a record that stretches back to the earliest epochs of solar system history. The largest of these dark regions is called Galileo Regio, a vast expanse stretching roughly 3,200 kilometers across the surface. Standing within Galileo Regio, an observer would see craters in every direction, their rims softened by time, but their forms still distinct against the grey terrain. The material composing the dark terrain is a mixture of water ice and some darker substance that has accumulated over eons. This darker material may be similar to the carbonaceous material found in primitive asteroids, debris delivered by countless impacts throughout Ganymede's history. The ice in these regions is old and has been darkened and altered by billions of years of exposure to Jupiter's radiation environment. Unlike the constantly renewed surfaces of Io and Europa, these dark regions preserve a record that reaches back nearly to the formation of the solar system itself. The grooved terrain presents a striking contrast to the ancient dark regions appearing brighter and showing far fewer impact craters. These lighter areas are crisscrossed by parallel ridges and grooves that can extend for hundreds of kilometers across the surface. The grooves typically measure a few kilometers wide and a few hundred meters deep, creating a texture visible in spacecraft images as fine parallel lines. The formation of this terrain required significant geological activity, suggesting that Ganymede was not always the quiet world it appears today. Scientists believe the grooved terrain formed when Ganymede's ice shell stretched and fractured, allowing warmer ice from below to rise up and create new surface. This process may be similar to what happens on Europa today, though it occurred in Ganymede's past rather than its present. The grooves likely formed along fault lines where the ice was pulled apart, with the parallel nature reflecting consistent stress directions during formation. Some regions show multiple sets of grooves crossing each other at different angles, recording different episodes of tectonic activity. The relative youth of the grooved terrain, perhaps a few billion years old rather than 4 billion, tells us that Ganymede experienced significant internal activity for some period after its formation. Whether this activity resulted from tidal heating, similar to what powers Io and Europa today, or from some other source of internal energy, remains a subject of scientific investigation. Ganymede receives less tidal heating than its inner neighbors, because it orbits farther from Jupiter and experiences less gravitational flexing. The Moon may have been more volcanically active early in its history, when radioactive elements in its interior were more abundant. One of the most remarkable features on Ganymede is a vast bright scar called the Tross crater, which shows evidence of an impact that punched through the surface layers. Impact craters on icy bodies often show different characteristics than craters on rocky worlds, because ice behaves differently than rock under extreme stress. Large impacts on Ganymede can excavate material from deep below the surface, revealing brighter ice that has not been darkened by radiation exposure. These bright ray craters stand out against the darker surrounding terrain, marking the sites of relatively recent impacts. Ganymede's interior structure is complex, with evidence suggesting multiple distinct layers stacked beneath the surface we can observe. At the very center sits an iron-rich core, similar in composition to Earth's core, though smaller in proportion to the Moon's overall size. Surrounding this core is a rocky mantle that comprises a significant fraction of Ganymede's total mass, heated by radioactive decay of elements within the rock. Above the rock lies what may be multiple layers of ice in different forms, with warmer ice below and colder ice at the surface. The detection of an internally generated magnetic field at Ganymede provided one of the most surprising discoveries about this moon. No other moon in the solar system generates its own magnetic field from internal processes. Earth's moon does not, nor do any of Saturn's moons or the other Galilean satellites. For a world to generate a magnetic field, it typically needs a liquid, electrically conducting layer that moves and churns in patterns that sustain the field. Ganymede's magnetic field suggests that its iron core remains at least partially liquid, even today, billions of years after the Moon's formation. The magnetic field Ganymede generates is only about 1% as strong as Earth's magnetic field, relatively modest by planetary standards, but extraordinary for a moon. This field creates a small magnetosphere around Ganymede, a bubble of protected space where the Moon's own field dominates over Jupiter's powerful magnetic influence. Charged particles from Jupiter's radiation belts interact with this magnetosphere, creating auroras near Ganymede's poles, similar to the northern and southern lights on Earth. These auroras appear as faint glowing ovals in ultraviolet observations, marking where particles follow field lines down toward the surface. The behavior of Ganymede's auroras provided unexpected evidence for yet another subsurface ocean in the Jupiter system. Scientists using the Hubble Space Telescope observed how the auroral ovals rock back and forth in response to Jupiter's rotating magnetic field, which washes over Ganymede regularly. If Ganymede were solid all the way through, the auroras would rock much more dramatically than if a conducting layer dampens the effect. The observed rocking is subdued in just the way we would expect if a salty ocean exists somewhere beneath the surface. This ocean is believed to lie sandwiched between layers of ice, rather than sitting directly beneath a single ice shell, as Europa's ocean does. The extreme pressures, deeper inside Ganymede, would force water into exotic high-pressure forms of ice that sink below liquid water. The resulting structure might consist of surface ice, then liquid ocean, then high-pressure ice, then rock, then the iron core at the center. This layer cake arrangement is unique among the known ocean worlds and raises interesting questions about how heat and materials might move through such a system. The depth and extent of Ganymede's ocean remain uncertain, but estimates suggest it could be up to 100 kilometers deep. If this estimate is correct, the ocean would contain more water than exists in all of Earth's surface oceans combined, despite being trapped between ice layers. The salt content of the water is unknown, though it must be present in sufficient concentration to make the ocean electrically conductive. What conditions exist at the boundaries between the ocean and the ice, above and below, is a question future missions may help answer. Ganymede possesses a thin atmosphere, though calling it an atmosphere almost seems generous given how sparse it is. Oxygen molecules exist in small quantities above the surface, created when charged particles from Jupiter's radiation belts break apart water ice molecules at the surface. This oxygen does not come from life processes as Earth's atmospheric oxygen does, but from the simple physics of radiation interacting with ice. The pressure of this atmosphere is only about 1/1,000,000th of Earth's atmospheric pressure, imperceptible to any instrument not specifically designed to detect it. The surface temperature on Ganymede varies from about -200 degrees Celsius in the polar regions to perhaps -120 degrees, where the sun shines most directly. These temperatures keep the surface ice frozen solid, harder than rock under these conditions, and stable over geological timescales. Day and night on Ganymede each last about 3.5 Earth days, as the moon is tidally locked with one face, always toward Jupiter. The hemisphere facing Jupiter never sees the planet set, while the opposite hemisphere never sees it rise. Orbiting above Ganymede and looking down, the two terrain types create a patchwork that tells a story of this moon's evolution over billions of years. The dark regions preserve the ancient bombardment history, a record of violence from the early solar system frozen in place and slowly darkened by time. The grooved terrain records a period of geological activity when internal heat or tidal stresses reshaped portions of the surface before the moon quieted again. Together, they reveal a world that has experienced multiple chapters in its long history. The fourth and final Galilean moon orbits beyond Ganymede, farther from Jupiter than any of its large siblings. This ancient world has remained largely unchanged for 4 billion years, its surface recording the full history of bombardment without the resurfacing that has erased craters on the other large moons. Callisto waits in the outer reaches of Jupiter's regular moon system, a quiet counterpart to the active worlds orbiting closer in. The outermost of Jupiter's 4 large moons traces a path so distant that Jupiter's tidal influence barely reaches it anymore. Callisto orbits nearly 2 million kilometers from Jupiter, taking almost 17 Earth days to complete a single trip around the giant planet. This distance makes all the difference in what kind of world Callisto has become over the eons since its formation. While its inner siblings experience tidal heating that drives volcanism, moves oceans, and reshapes surfaces, Callisto has remained cold and quiet. The surface of Callisto presents one of the most heavily cratered landscapes in the entire solar system, a record of bombardment stretching back 4 billion years. Every region visible in spacecraft images is pockmarked with impact craters, large and small, overlapping and adjacent, ancient beyond easy comprehension. Unlike Europa, where craters are erased by geological activity, or Io, where volcanic deposits bury them, Callisto preserves its craters indefinitely. The surface we see today looks much as it did when the heavy bombardment of the early solar system finally tapered off. Approaching Callisto, the moon appears dark compared to Europa's brilliant white, or even Ganymede's mottled but brighter terrain. The surface reflects only about 20% of the sunlight that falls on it, making Callisto one of the darker objects among the icy moons. This darkness comes from rocky material mixed thoroughly with the ice, accumulated over billions of years of small impacts that delivered carbonaceous dust. The ice and rock have never separated into distinct layers as they did on Ganymede, remaining mixed together throughout the moon's history. The lack of differentiation inside Callisto tells us something important about how this moon formed and evolved differently from its siblings. Ganymede, with its distinct iron core and rocky mantle and ice shell, clearly melted and separated into layers early in its history. Callisto's interior appears much more uniform, with ice and rock mixed together, without clear boundaries between them. This difference suggests that Callisto never got hot enough to melt thoroughly, perhaps because it formed more slowly or because it experienced less tidal heating. The most striking feature on Callisto's surface is a massive impact scar called Valhalla, named after the Great Hall of Norse mythology. Valhalla consists of a bright central region about 600 kilometers across, surrounded by concentric rings that extend outward for nearly 2,000 kilometers in all directions. These rings represent frozen ripples in the icy crust, waves that spread outward from the impact site and were preserved when the ice solidified again. From above, Valhalla resembles a bullseye or target, the rings marking the path of energy radiating away from ground zero. The impact that created Valhalla occurred billions of years ago, when a large asteroid or comet struck the icy surface with tremendous force. The energy of the collision sent shockwaves rippling through the crust, temporarily fluidizing the ice and allowing it to flow like a liquid. As these waves propagated outward, the ice behind them refroze, capturing the ring pattern we see today in permanent form. Similar multi-ring basins exist on other icy bodies in the outer solar system, but Valhalla remains among the most well-preserved and clearly defined. Another large impact basin, called Asgard, sits elsewhere on Callisto's surface, showing a similar but smaller ring structure. Asgard spans about 1,600 kilometers across, its concentric rings still visible despite billions of years of subsequent smaller impacts. The presence of multiple large impact basins reminds us that the early solar system was a violent place, with large objects still abundant and collisions common. Callisto's surface serves as a record of that violent era, preserved in ice that has remained largely unchanged since. Between the large basins, Callisto's surface is covered with craters of all sizes, from features hundreds of kilometers across down to the smallest pits visible in spacecraft images. The craters appear somewhat softened compared to those on rocky worlds like Mercury or Earth's moon, their rims rounded and their floors flattened by processes specific to ice. Ice slowly deforms under its own weight over geological timescales, a process called viscous relaxation, gradually smoothing out topographic features. The larger craters on Callisto show more relaxation than smaller ones, their greater depths causing faster deformation. One peculiar feature found across Callisto's surface consists of small, bright spots that dot the landscape between craters. These spots may represent the tops of ice knobs or spires, left behind as surrounding darker material eroded away over billions of years. The process involves ice sublimating away, changing directly from solid to gas, while the rocky material mixed with it remains behind as a lag deposit. Over vast stretches of time, areas where ice is protected remain elevated, while surrounding areas wear down, creating the spotted appearance. Callisto's lack of geological activity means that no internal heat is erasing or modifying the surface features we observe. The moon is not entirely cold inside. Some heat from radioactive decay of elements in the rocky fraction still exists, but this is not enough to drive any surface activity. No volcanoes erupt here. No ice tectonics shift the surface around. No ocean materials well up through cracks in the crust. Callisto is a frozen museum displaying its ancient surface to anyone patient enough to travel out and observe. Despite this apparent geological death, evidence suggests that even cold, quiet Callisto may harbor a subsurface ocean. Magnetic field measurements from the Galileo spacecraft revealed the same type of induced magnetic signature found at Europa and Ganymede. For this signature to exist, Callisto must contain an electrically conducting layer somewhere in its interior, and liquid salt water remains the most plausible candidate. How an ocean can exist inside such a geologically inactive body remains somewhat puzzling, requiring either greater internal heat than expected or some form of antifreeze in the water. The potential ocean inside Callisto would likely lie much deeper than Europa's ocean, hidden beneath perhaps 150 to 200 kilometers of ice and ice rock mixture. This depth places the ocean far from any potential energy sources at the surface and limits interaction between the ocean and the space environment. If the ocean exists, it may persist because of ammonia or other antifreeze compounds that lower the melting point of water significantly. Such a deep, isolated ocean presents different conditions than the potentially more dynamic oceans of Europa or Ganymede. Callisto's position outside the orbital resonance that links Io, Europa, and Ganymede explains much about why this moon is so different from its siblings. The resonance keeps the inner three moons in their synchronized dance, maintaining the slightly elliptical orbits that enable tidal heating. Callisto, too far out to be captured in this resonance, has settled into a nearly circular orbit that generates minimal tidal flexing. Without this heat source, the moon was never warmed enough to differentiate fully or to drive the geological activity that characterizes the inner moons. The surface temperature on Callisto averages around -140 degrees Celsius, somewhat warmer than Ganymede's poles, but still tremendously cold by any earthly standard. Day and night each last about 8 Earth days, as Callisto's slow orbit matches its slow rotation in the typical tidally locked arrangement. Jupiter appears much smaller from Callisto than from the inner moons, spanning only about 4 degrees of sky, compared to over 20 degrees seen from Io. The giant planet's influence is still felt, but it no longer dominates the sky as it does for the closer companions. Looking across Callisto's ancient surface, the scene has a quality of timelessness found in few other places in the solar system. The craters visible today are the same craters that existed 4 billion years ago, slowly softening but never erased, never buried, never reformed. Light from the distant sun falls on landscapes that have not changed in any significant way since before life existed on Earth. If a spacecraft from some previous civilization had photographed Callisto billions of years ago, the images would look remarkably similar to what we see today. The 4 Galilean moons, Io, Europa, Ganymede, and Callisto, present a gradient of activity and age that teaches us how distance from a planet shapes a moon's evolution. Io, closest in, is the most active body we know. Europa, slightly farther, maintains an ice-covered ocean with hints of ongoing activity. Ganymede shows evidence of past activity now quieted. Callisto, farthest out, appears never to have been significantly active at all. This pattern emerges from the orbital resonance that connects the inner 3 moons while leaving Callisto on its own. The dance these moons perform around Jupiter is not random, but precisely choreographed by gravity over billions of years. Understanding this dance, the orbital resonance that keeps the inner 3 moons synchronized and heated, reveals why such different worlds can orbit so close together. The relationship between orbital periods and internal heat connects the distant realm of orbital mechanics to the volcanoes on Io and the oceans beneath Europa's ice. 3 of Jupiter's large moons move around the planet in a pattern so precisely timed that their orbital periods form exact whole number ratios with each other. For every single orbit that Ganymede completes around Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4. This relationship, called an orbital resonance, has persisted for billions of years and continues today with the same mathematical precision as when it first established. The consequences of this cosmic synchronization explain why some moons blaze with volcanic activity, while others maintain hidden oceans beneath their ice. The timing involved in this resonance becomes clear when we look at the actual orbital periods of each moon. Io takes approximately 1.77 Earth days to complete a single orbit around Jupiter, circling the giant planet in just under 43 hours. Europa takes about 3.55 Earth days, essentially twice as long as Io. Ganymede completes its more distant orbit in approximately 7.15 days, twice Europa's period and 4 times Io's. Watching this system from a vantage point above Jupiter's North Pole, the 3 moons would trace their paths like the hands of a complex clock. Io would race around the innermost track, completing a full circuit, while Europa finished half of one and Ganymede finished only a quarter. The moons line up in certain configurations regularly, then separate, then return to those configurations again in predictable intervals. This dance has no conductor, no external force keeping time. Gravity alone maintains the pattern with extraordinary precision. The orbital resonance did not exist from the beginning of the Jupiter system, but developed over millions of years through gravitational interactions. When the moons first formed, their orbital periods were likely similar to today, but not precisely synchronized. As they orbited, gravitational tugs during close approaches gradually adjusted their orbits, pushing them toward the resonant configuration. Once locked into resonance, the system became self-maintaining, with each deviation corrected by subsequent gravitational interactions. The mathematician Pierre-Simon Laplace first recognized and described this resonance in the late 1700s, when orbital mechanics was still a developing field. Laplace showed that the relative positions of the 3 moons follow a specific pattern that repeats indefinitely over time. No matter when you observe the system, the angular positions of the 3 moons will satisfy a particular mathematical relationship. This predictability allowed astronomers to calculate where each moon would be at any future time with remarkable accuracy. What makes the resonance so significant for the moons themselves is how it prevents their orbits from becoming perfectly circular. In the absence of other influences, an orbiting body naturally tends toward a circular orbit, the lowest energy configuration for a given orbital distance. The regular gravitational tugs that maintain the resonance also prevent this settling, keeping each orbit slightly elliptical. These elliptical orbits are the key to understanding why Io is the most volcanic body in the solar system. An elliptical orbit means the moon's distance from Jupiter changes throughout each orbit, approaching closer at one point and receding farther at another. When the distance changes, the strength of Jupiter's gravitational pull changes too, and this varying pull creates tidal forces within the moon. The moon is literally stretched and compressed as it moves through its orbit, with the effect strongest at closest approach and weakest at farthest point. This continuous flexing generates heat through internal friction, warming the moon from within. The amount of tidal heating each moon receives depends on several factors, with distance from Jupiter being among the most important. Io, orbiting closest, experiences the strongest tidal forces and the most heating, which explains its extreme volcanic activity. Europa, somewhat farther out, receives less heating, but apparently enough to maintain a liquid water ocean beneath its ice. Ganymede, farther still, gets even less tidal heat, though perhaps enough to maintain the deep ocean suggested by magnetic field observations. Callisto's absence from the resonance explains why it differs so dramatically from its inner siblings despite similar size and composition. Orbiting beyond the resonance, Callisto has settled into a nearly circular orbit that generates minimal tidal heating. Without this internal energy source, Callisto remained cold, never differentiating fully into distinct layers, never developing the geological activity that characterizes the inner moons. The resonance is like a heater that warms 3 houses while leaving the 4th cold, simply because of where it stands. The stability of this resonance over billions of years is one of its most remarkable properties. Once the moons locked into their current configuration, the resonance became extremely difficult to disrupt. External influences like passing asteroids or the gravity of the sun might shift the orbit slightly, but the resonance corrects itself. This self-correcting nature means the synchronized dance has likely continued with little change since the early solar system, warming Io and Europa for longer than complex life has existed on Earth. Similar orbital resonances exist elsewhere in the solar system, though none with quite the same dramatic consequences for surface activity. Some of Saturn's moons show resonant relationships, and resonances play important roles in shaping the structure of the asteroid belt. Neptune's moon Triton may have disrupted resonances among Neptune's original moons when it was captured from the outer solar system. The Jupiter system's resonance stands out for its completeness and for the visibility of its effects on the moons themselves. The energy involved in maintaining the resonance ultimately comes from Jupiter's rotation, transferred to the moons through gravitational interactions over billions of years. Jupiter rotates faster than the moon's orbit, completing a day in less than 10 hours. And this rotational energy slowly converts to orbital energy and heat. The process is gradual enough that Jupiter's rotation has not slowed noticeably over the age of the solar system. The giant planet has energy to spare, and the moons draw from this reserve to power their internal activity. Looking at the three moons from above, as they trace their synchronized paths, the elegance of the pattern belies the violent consequences playing out within. Io's hundreds of volcanoes, Europa's shifting ice and hidden ocean, Ganymede's ancient grooved terrain. All these features trace back to the simple gravitational arithmetic of 1 to 2 to 4. The universe often hides its most profound connections in numerical relationships, waiting for observers patient enough to notice and understand them. The mechanism by which this orbital dance generates heat within the moons deserves closer examination, as it explains not just activity levels, but also the specific features we observe on each world. Tidal heating is a subtle but powerful process, capable of melting rock inside Io and maintaining liquid water inside Europa across billions of years of time. Understanding how gravitational flexing converts to thermal energy reveals the engine that drives these distant worlds. The force that heats Io's interior and maintains Europa's ocean is the same force that raises the tides in Earth's oceans, though operating with far greater intensity in the Jupiter system. Tidal forces arise whenever gravity pulls more strongly on one side of an object than on the other, creating a stretching effect across the body. Jupiter is so massive and Io is so close that this stretching effect is hundreds of times stronger than anything experienced by Earth. The consequences of this stretching explain why a moon in the cold outer solar system can have molten rock beneath its surface. Gravity decreases with distance, following a precise mathematical relationship that Isaac Newton first described centuries ago. When Jupiter's gravity reaches towards Io, the near side of the moon, the side facing Jupiter, feels a stronger pull than the center, and the center feels a stronger pull than the far side. This difference in pull creates a tidal bulge, stretching Io slightly along the line connecting it to Jupiter. A matching bulge appears on the far side, where material is pulled less strongly than the center and effectively bulges outward. If Io orbited Jupiter in a perfectly circular path, these tidal bulges would remain fixed in position, always pointing toward and away from Jupiter. The Moon would be stretched, but the stretching would not change, and no friction would be generated. The orbital resonance prevents this by keeping Io's orbit slightly elliptical, which means the distance to Jupiter changes throughout each 42-hour orbit. As the distance changes, the strength of the tidal pull changes, and the tidal bulges grow and shrink accordingly. This changing deformation is what generates heat inside Io and its neighboring moons. As the Moon is stretched and compressed repeatedly, material inside must move against other material, creating friction. This friction converts orbital energy into thermal energy, warming the interior with each cycle through the orbit. The heating is concentrated in areas where deformation is greatest, which likely means Io's mantle experiences more heating than its core. The amount of heat generated by this process inside Io is staggering, exceeding 100 trillion watts by some estimates. To put this in perspective, all of Earth's volcanoes, geysers, hot springs, and internal heat flow combined add up to roughly 40 trillion watts. Io, a moon only slightly larger than our own moon, produces more internal heat than our entire geologically active planet. This heat must escape somehow, and the escape route is through the 400 or more active volcanoes that dot Io's tormented surface. The surface of Io rises and falls by roughly 100 meters during each orbit as the tidal bulges grow and shrink with changing distance to Jupiter. For comparison, Earth's solid surface rises and falls by only about 30 centimeters due to the Moon's tidal influence, an effect we cannot perceive without precise instruments. Io's 100-meter flexing is roughly 300 times greater, occurring every 42 hours rather than every day. This continuous working of the Moon's interior has persisted for billions of years without pause. Europa experiences similar tidal heating, though less intense due to its greater distance from Jupiter and the correspondingly weaker tidal forces. The heating is sufficient to maintain liquid water beneath the ice shell, but not enough to generate the massive volcanic activity seen on Io. This intermediate level of heating creates a world where ice can crack and shift, where material from below can reach the surface, but where the surface remains predominantly frozen. Europa's ocean is the result of a careful balance between heat generated within and heat radiated to space. The thickness of Europa's ice shell likely reflects this balance between internal heating and surface cooling. More heating would thin the ice or melt it entirely. Less heating would allow the ocean to freeze solid from above. Current estimates suggest the ice shell is 10 to 25 kilometers thick, maintained at this equilibrium by the steady input of tidal heat from below. The chaos terrain and fracture patterns we observe may represent variations in this balance, places where heat flow is slightly higher and the ice responds accordingly. Ganymede receives less tidal heating than Europa, both because it orbits farther from Jupiter and because its resonance with the inner moons is weaker. The heating may be just enough to maintain a deep ocean sandwiched between layers of ice, but not enough to produce significant surface activity. Ganymede's grooved terrain tells us the Moon was more active in the past, perhaps when radioactive heating supplemented tidal heating, or when the orbital configuration differed from today. The current quiet state reflects the reduced energy input at this greater distance. The distribution of tidal heating within a moon is not uniform, creating interesting patterns of activity that we can observe on the surfaces. On Io, some regions appear more volcanically active than others, suggesting that heat concentrates in certain areas of the interior. These hotspots may mark places where the mantle flows differently, or where the crust is thinner, allowing heat to escape more readily. The complex interplay between interior heating and surface volcanism creates the ever-changing landscape that spacecraft have documented. Tidal heating differs from radioactive heating, the other major source of internal heat in planetary bodies, in several important ways. Radioactive heating comes from unstable atoms deep in a planet's interior that decay over time, releasing energy in the process. This heating decreases as the radioactive elements are exhausted, meaning ancient worlds have less radioactive heat than young ones. Tidal heating, in contrast, can continue indefinitely as long as the orbital configuration remains in resonance, providing a potentially eternal energy source. The interaction between tidal heating and internal structure creates feedback loops that shape how moons evolve over time. A moon that heats up becomes softer and more easily deformed, which can actually increase the rate of heating in a runaway process. Conversely, a moon that cools down becomes stiffer and less easily deformed, reducing heat generation and allowing further cooling. Io and Europa appear to have reached stable equilibrium states, while other moons may have cooled past the point where tidal heating can restart. Scientists have developed sophisticated computer models to understand how tidal heating operates inside these moons, but many details remain uncertain. The exact distribution of heat generation depends on internal structure, composition, and material properties that we cannot measure directly. Different models produce different predictions about where oceans exist, how thick ice shells are, and whether geological activity continues today. Future spacecraft missions carrying instruments designed to probe moon interiors will help resolve these questions. The realization that tidal heating could maintain liquid water in the outer solar system transformed our understanding of where life might exist beyond Earth. Before this recognition, the outer solar system seemed too cold and dark for liquid water, limiting the search for life to planets closer to the Sun. Tidal heating provides an alternative energy source that operates independently of sunlight, opening up possibilities throughout the cosmos. Any moon in an orbital resonance around a sufficiently massive planet could potentially harbor a liquid water ocean. Beyond the 4 large moons, heated by their orbital dance, Jupiter holds dozens of smaller companions in orbits that tell different stories. Closer to Jupiter than Io, small irregular moons orbit among the planet's faint rings, their surfaces battered by the intense radiation environment. These inner moons represent a different category entirely, formed from debris rather than in a circumplanetary disk like the Galilean moons. Between Jupiter and the orbit of Io, a collection of small moons traces paths through one of the most extreme environments in the solar system. These inner moons, Amalthea, Thebe, Metis, and Adrastea, orbit so close to Jupiter that the giant planet's radiation belts bombard their surfaces constantly. Each of these small worlds is irregular in shape, their masses too low for gravity to pull them into spheres, looking more like potatoes or lumpy rocks than the round moons we typically imagine. Their proximity to Jupiter also means they are intimately connected with the planet's faint ring system. Amalthea is the largest of these inner moons, stretching approximately 250 kilometers along its longest axis and about 128 kilometers along its shortest. This elongated shape keeps one end always pointed toward Jupiter, locked in place by tidal forces, just as the larger moons are locked with one face perpetually toward the giant planet. The surface appears reddish in color, making Amalthea one of the reddest objects in the entire solar system, even redder than Mars or Io. The source of this distinctive color likely involves sulfur compounds, perhaps originating from the nearby volcanic activity on Io. The surface of Amalthea shows several large impact craters, despite the moon's small size making it a relatively small target in the vastness of space. The two largest craters, Pan and Gaia, measure roughly 175 kilometers in diameter respectively, significant features on a body only a bit longer than that. Mountains or ridges have also been identified, reaching perhaps 20 kilometers high on a moon where the highest point is barely 130 kilometers from the center. Gravity on Amalthea is so weak that an astronaut could jump entirely off the surface and into orbit with a strong enough leap. One of the most mysterious aspects of Amalthea is that it appears to radiate more heat than it receives from the sun. Infrared observations detected this excess heat emission, suggesting some internal energy source that scientists cannot fully explain. The most likely explanation involves Jupiter's powerful magnetic field, which may induce electrical currents inside the moon as it orbits through the field. These induced currents would generate resistive heating, literally cooking the moon from within through electromagnetic induction. Thebe orbits just outside Amalthea, a smaller, irregular moon approximately 100 kilometers across at its widest point. Like Amalthea, Thebe shows an irregular shape and a surface marked by impact craters. Though we have less detailed information about its features, the surface appears grayish compared to Amalthea's red, suggesting different compositions or different histories of radiation exposure. Thebe is notable for its connection to one of Jupiter's faint rings, a structure called the Thebe-Gossamer ring that extends outward from the moon's orbit. Metis and Adrastea are the innermost of Jupiter's known moons, orbiting closer to the planet than any of the others. Metis measures only about 40 kilometers across, while Adrastea is smaller still at roughly 20 kilometers, making both among the smallest known moons in the solar system. These tiny worlds orbit so fast that they actually complete their circuits around Jupiter in less time than Jupiter takes to rotate once. From a vantage point on Jupiter's cloud tops, Metis and Adrastea would appear to rise in the west and set in the east, moving backward across the sky. Both of these innermost moons orbit within Jupiter's main ring, and their presence there is not coincidental. The ring particles are believed to come largely from these moons, knocked off their surfaces by micrometeoroid impacts that throw dust into orbit. This material then slowly spirals inward toward Jupiter, eventually falling into the planet's atmosphere, while new material is continuously generated from the moons. The inner moons effectively supply their own rings, a system where the rings persist only because the moons keep replenishing them. Jupiter's ring system is far fainter than Saturn's famous rings, invisible to casual observation, and discovered only when the Voyager spacecraft flew past in 1979. The main ring is about 7,000 kilometers wide, but only 30 kilometers or so thick, a thin sheet of tiny particles orbiting in Jupiter's equatorial plane. Unlike Saturn's rings, which are made of water ice chunks ranging from pebbles to small buildings, Jupiter's rings are made of dark dust particles, mostly microscopic in size. These particles absorb light rather than reflecting it, which is why the rings are so difficult to observe. Two broader, fainter rings extend beyond the main ring, named the Amalthea-Gossamer ring and the Thebe-Gossamer ring, after their source moons. These Gossamer rings are even thinner and more tenuous than the main ring, visible only under specific lighting conditions when sunlight scatters forward through the dust. The material in these rings also originates from impacts on Amalthea and Thebe, knocked loose and spread along the moon's orbital paths. Over time, the dust spirals inward, creating the broad sheets that give these rings their name. The radiation environment near these inner moons is extraordinarily harsh, far more intense than anything experienced in the inner solar system. Jupiter's magnetic field is the strongest planetary magnetic field in the solar system, roughly 20,000 times stronger than Earth's, and it traps charged particles in radiation belts that make Earth's Van Allen belts seem gentle by comparison. Any spacecraft visiting these regions must be specially hardened against radiation, and organic molecules would be quickly destroyed by the constant bombardment. The inner moons have no protection from this environment. Their surfaces continually processed by energetic particles. The four inner moons all orbit within Jupiter's Roche limit, the distance inside which tidal forces would tear apart a liquid body held together only by gravity. These moons survive because they are solid rock and ice, held together by their material strength rather than their own gravity. A larger moon in these orbits would indeed be torn apart by Jupiter's tidal forces, its materials spreading out to form more rings. The small size of the inner moons is directly related to their ability to exist so close to the giant planet. Viewing Jupiter's inner moon system requires spacecraft observations, as these small bodies are lost in the glare of Jupiter when observed from Earth. The Galileo mission provided the most detailed images we have of Amalthea and the smaller inner moons, though even these images show limited resolution given the small target sizes. Future missions may provide better views, though the challenging radiation environment makes prolonged observation difficult. For now, these small moons remain somewhat mysterious, their surfaces seen only in glimpses. The formation of these inner moons likely differs from the formation of the Galilean moons, which grew from material in a disk around young Jupiter. The inner moons may be fragments of larger bodies that strayed too close to Jupiter and were broken apart, with these pieces settling into stable orbits. Alternatively, they may have formed from debris generated by collisions between objects in the Jupiter system, accumulated into their current irregular shapes. Their compositions, so far as we can determine, suggest rocky material mixed with some ice, similar to objects from the asteroid belt. Far beyond these close companions, at distances that dwarf even Callisto's orbit, dozens more moons trace their paths through the space around Jupiter. These distant irregular moons follow orbits quite different from the orderly paths of the Galilean satellites, tilted and elongated, and sometimes even retrograde. Their origins lie not in formation around Jupiter, but in capture from elsewhere in the solar system, making them immigrants to the Jupiter system rather than native residents. The distant reaches of the Jupiter system harbor a scattered population of small moons, following orbits unlike those of the famous Galilean satellites. These irregular moons, numbering over 80 at current count, orbit at vast distances from Jupiter in paths that are tilted, elliptical, and often retrograde, meaning they travel opposite to Jupiter's rotation direction. Most are small, measuring less than 5 kilometers across, rocky remnants of a more chaotic time in solar system history. Their presence tells us that Jupiter did not simply form its own moons, but also captured wanderers from the broader solar system. What makes an orbit irregular is the combination of high inclination, significant eccentricity, and often retrograde motion relative to Jupiter's rotation. The regular moons, including the 4 Galilean satellites and the inner small moons, all orbit in paths that lie close to Jupiter's equatorial plane, nearly circular and in the same direction Jupiter rotates. The irregular moons break all these rules, tilting dramatically relative to the equator, following elongated elliptical paths, and frequently orbiting backward. These characteristics identify them as captured objects rather than moons that formed in place. The irregular moons cluster into several groups or families, each named after a prominent member, with similar orbital characteristics suggesting common origins. The Himalaya group orbits prograde at distances of about 11 to 12 million kilometers from Jupiter, with orbital periods of around 250 days. The Calm group, Ananke group, and Pasiphae group all orbit retrograde at even greater distances, some taking more than 2 Earth years to complete a single orbit. These groupings suggest that the moons in each family were once parts of a single larger object that broke apart after capture. Himalaya itself is the largest of the irregular moons, measuring about 170 kilometers in diameter, large enough to be roughly spherical in shape. Himalaya was discovered in 1904 by Charles Dillon Perrine at Lick Observatory in California, making it the first irregular moon of Jupiter to be found. The surface appears dark and grayish, similar to carbonaceous asteroids found in the outer asteroid belt, supporting the idea that Himalaya originated there. Several smaller moons share Himalaya's orbital characteristics, likely fragments broken off during the capture event or from subsequent collisions. The retrograde groups contain more members than the prograde groups, which seems counterintuitive, but actually reflects the physics of gravitational capture. When an object passes through Jupiter's gravitational influence, retrograde capture is more likely because retrograde orbits are more stable against perturbations from the Sun's gravity. Objects on retrograde paths are moving opposite to Jupiter's orbit around the Sun, which creates conditions where capture and long-term stability are more probable. The predominance of retrograde irregular moons throughout the outer solar system reflects this capture asymmetry. The process of capturing a moon requires something to slow the incoming object enough that it cannot escape Jupiter's gravitational pull. An object flying past Jupiter on a hyperbolic trajectory, moving too fast to be captured, needs to lose energy somehow if it is to become a permanent resident. This energy loss could come from interactions with a primordial gas disk around young Jupiter, from collisions with existing material or moons, or from three-body interactions involving the Sun. The exact mechanisms for capturing the irregular moons remain subjects of ongoing research. Once captured, The new moons would have followed different orbits than we observe today, with subsequent gravitational perturbations and collisions reshaping the population. Collisions between captured objects could have fragmented larger bodies into the families we observe, producing multiple smaller moons from single original captures. The distribution of sizes and orbits we see today represents billions of years of evolution since the initial capture events. The outer reaches of Jupiter's gravitational influence have been a dynamic environment where moons have come, gone, and multiplied over eons. The outermost irregular moons orbit so far from Jupiter that the planet appears as little more than a bright star from their surfaces. Moons, in the Pasiphae group, for example, orbit at average distances of about 23 million kilometers, with orbital periods exceeding 700 Earth days. At these distances, Jupiter's gravitational influence is weak, and the Sun's gravity significantly affects the Moon's orbits over time. The boundary between a moon of Jupiter and an independent asteroid becomes almost philosophical at these extremes. One particularly interesting irregular moon, discovered in 2018, orbits in a region where it shouldn't exist according to simple dynamical arguments. Valetudo, named after Jupiter's great-granddaughter in Roman mythology, follows a prograde orbit, but does so at distances where the retrograde moons dominate. This orbit crosses the paths of retrograde moons, traveling in the opposite direction, creating a high probability of eventual collision over astronomical timescales. Valetudo may be a fragment from a larger object that was destroyed in just such a collision, or it may be doomed to meet a similar fate in the future. The irregular moons are too small and distant to see in any detail from Earth-based telescopes, appearing as moving points of light rather than resolved disks. What we know about their sizes comes from their brightness, combined with assumptions about how reflective their surfaces are. Most appear dark, reflecting only a few % of the light that falls on them, suggesting compositions similar to primitive asteroids. Their surfaces are probably covered in impact craters accumulated over billions of years, though we have no direct images to confirm this. New irregular moons continue to be discovered as telescope technology improves and systematic surveys become more thorough. The count of known Jupiter moons increased from 67 in 2017 to 95 by 2023, with most new discoveries being small, irregular moons in the outer reaches. Some of these newly found moons are only 1 or 2 kilometers across, right at the edge of what current technology can detect at Jupiter's distance. There may be hundreds or thousands more, even smaller objects orbiting Jupiter that we simply cannot see yet. The irregular moons provide important evidence about conditions in the early solar system, particularly the chaotic period when the giant planets may have migrated from their formation locations. Models of planetary migration suggest that Jupiter, Saturn, Uranus, and Neptune all moved significantly during the first few 100 million years, disrupting the orbits of countless small bodies. Some of these disrupted objects would have been captured as irregular moons, while others were flung into the inner solar system or ejected entirely. The population of irregular moons we observe today represents survivors of this tumultuous period. Understanding the irregular moons helps us connect the Jupiter system to the broader history of the solar system and its formation. These small, dark, distant objects are not the dramatic worlds that Io and Europa represent, but they carry information about processes that shaped everything we see today. Their compositions link them to the primitive building blocks of planets. Their orbits record the violence of planetary migration. And their family groupings reveal the ongoing collisions that continue to reshape the outer solar system. The irregular moons are messengers from a different era, captured and preserved in Jupiter's gravitational embrace. Behind all these moons, both regular and irregular, lies the question of how Jupiter itself formed and how it came to host such a diverse family of companions. The giant planet and its largest moons emerged from the same disk of gas and dust that formed the Sun itself, a process that unfolded over millions of years in the earliest epoch of our solar system. The birth of Jupiter and its moon system stretches back more than 4.5 billion years, to a time when the solar system was a disk of gas and dust swirling around a newly formed sun. Within this disk, material slowly accumulated into larger and larger clumps, building up the planets that orbit the Sun today through a process of gradual accretion. Jupiter formed faster and grew larger than any other planet, capturing enormous amounts of gas before the disk dissipated, becoming the giant we observe today. Around this growing giant, a smaller disk of gas and dust developed, and from this circumplanetary disk, the Galilean moons would emerge. The location where Jupiter formed played a crucial role in determining its size and the composition of its moons. Beyond a distance from the Sun, called the frost line, temperatures were cold enough for water and other volatile compounds to freeze into solid ice. This meant more solid material was available to build planet cores beyond this distance, and Jupiter formed where both rock and ice could accumulate. The same ice that helped Jupiter grow large also provided the raw material for its icy outer moons, explaining why Ganymede and Callisto contain so much frozen water. Jupiter's core likely formed first, a rocky and icy body that accumulated from smaller pieces, colliding and sticking together over millions of years. Once this core reached a certain size, perhaps 10 to 15 times the mass of Earth, it began pulling in gas from the surrounding disk. The gas accumulated slowly at first, but eventually reached a tipping point where the process accelerated dramatically, drawing in vast quantities of hydrogen and helium. Within perhaps 100,000 years after reaching this threshold, Jupiter had captured most of its current mass, becoming a giant planet. The circumplanetary disk that formed around Jupiter was like a miniature version of the solar system's protoplanetary disk, with material orbiting the young planet rather than the Sun. This disk was fed by material falling inward from the larger solar nebula, creating a dynamic environment where new material constantly arrived. Within this disk, the same processes that built planets around the Sun began to build moons around Jupiter. Particles stuck together to form larger aggregates, which grew into moonlets, which eventually became the Galilean moons. The composition of the Galilean moons reflects the temperature gradient within this circumplanetary disk, with inner regions warmer than outer regions. Io, forming closest to young Jupiter, was too warm for ice to remain solid, so it accumulated mostly rocky material. Europa, forming slightly farther out, incorporated some ice, but still has a significant rocky fraction. Ganymede and Callisto, forming in the cooler outer regions of the disk, accumulated more ice relative to rock, This gradient mirrors the composition gradient in the solar system, where rocky planets formed close to the Sun and icy bodies formed farther out. The current density of each Galilean moon provides direct evidence for this compositional gradient. Io has a density of about 3.5 grams per cubic centimeter, similar to Earth's moon, and indicating a rocky composition. Europa's density of about 3 grams per cubic centimeter suggests rock with some ice mixed in. Ganymede and Callisto have densities around 1.8 to 1.9 grams per cubic centimeter, indicating nearly equal mixtures of rock and ice. These density measurements, obtained by tracking how spacecraft are gravitationally deflected during flybys, confirm the story told by formation models. The formation of the Galilean moons may not have been a simple, linear process, but could have involved episodes of destruction and rebuilding. Models suggest that early generations of moons might have formed and then spiraled into Jupiter due to interactions with the gas disk. New moons would form from the disk material, only to potentially suffer the same fate. The 4 Galilean moons we see today may be survivors from the final stages of this process, forming after the disk had thinned enough that migration into Jupiter was no longer inevitable. The timing of moon formation, relative to Jupiter's growth, also affected their eventual properties. Moons that formed while Jupiter was still growing would have experienced different conditions than moons that formed after Jupiter had finished accumulating mass. The heat generated by infalling material onto young Jupiter would have affected temperatures throughout the circumplanetary disk. Later forming moons would have experienced cooler conditions, potentially explaining differences in internal structure between the Galilean satellites. Callisto's lack of internal differentiation presents a puzzle that relates to its formation history. Unlike Ganymede, which fully separated into layers of ice and rock, Callisto appears only partially differentiated, with its interior remaining largely mixed. This difference could mean Callisto formed more slowly, never generating enough heat from accretion to fully melt its interior. Alternatively, Callisto may have formed from smaller building blocks that released less energy upon collision, keeping temperatures low enough to prevent complete differentiation. The orbital resonance among Io, Europa, and Ganymede may have developed during or shortly after their formation, as gravitational interactions adjusted their orbits over time. Alternatively, the resonance may have formed later, as the moon's orbits evolved due to tidal interactions with Jupiter. The exact history of the resonance formation affects predictions about how the moon's orbits will change in the future. Understanding whether the resonance is primordial or developed later remains an active area of research. The irregular moons arrived later than the Galilean moons, captured from the surrounding solar system rather than forming from Jupiter's circumplanetary disk. These capture events likely occurred during the first few 100 million years of solar system history, when more small bodies were available to be captured. The chaotic orbital changes of the giant planets during this period would have enhanced capture opportunities, sending countless objects through Jupiter's sphere of influence. Those that lost enough energy to become bound formed the scattered population of irregular moons we observe today. Jupiter's formation also influenced the broader architecture of the solar system, affecting what objects exist and where they orbit. The giant planet's gravity stirred up the asteroid belt, preventing a fifth terrestrial planet from forming between Mars and Jupiter. Jupiter may also have migrated inward during the early solar system, before moving back out, scattering objects throughout the system. The moons of Jupiter record not just local history, but also bear witness to processes that shaped everything from the asteroid belt to the Kuiper belt. Today, Jupiter and its moons have long since settled into their current configuration, the violent birth pangs of the early solar system billions of years in the past. The orbital resonance continues its clockwork precision. Io's volcanoes erupt and rebuild the surface. Europa's ice shell cracks and heals, and the irregular moons trace their slow paths through the outer reaches. This system would remain invisible and unknown to human observers until a few centuries ago, when new technology first revealed the 4 largest moons as points of light moving around a distant wandering star. For thousands of years, Jupiter appeared to human observers as nothing more than a bright wandering star, its moons far too faint to see with the naked eye. Ancient astronomers tracked Jupiter's motion against the background stars, noting how it moved along the same band of sky as the Sun and the other known wandering stars we now call planets. They could not know that this point of light was a giant world with nearly 100 moons orbiting around it, a solar system in miniature. The revelation that Jupiter hosted its own companions would wait until a new invention allowed observers to see what had always been there. In the year 1609, reports of a Dutch invention that made distant objects appear closer reached ears throughout Europe, including those of an Italian professor of mathematics named Galileo Galilei. Galileo quickly built his own version of this instrument, which we now call a telescope, and turned it toward the night sky. What he saw in those first observations would change human understanding of the cosmos forever, revealing a universe far more complex and interesting than anyone had imagined. Among his many discoveries, the moons of Jupiter would prove especially significant. Galileo first observed Jupiter through his telescope on the 7th of January, 1610, and noticed 3 small points of light close to the planet, arranged in a line. He initially thought these might be background stars, but over subsequent nights of observation, their positions changed relative to Jupiter. By January 15th, Galileo had identified a 4th point of light and realized that all 4 were orbiting Jupiter itself. This discovery provided direct evidence that not everything in the cosmos orbited Earth, supporting the controversial idea that Earth might not be the center of everything. The 4 moons Galileo discovered are now called the Galilean moons in his honor: Io, Europa, Ganymede, and Callisto. Galileo himself called them the Medicean stars, after his patrons the Medici family who ruled Florence, and whose support he needed for his career. A German astronomer named Simon Marius claimed to have discovered the moons independently around the same time, and proposed the mythological names we use today. The names come from figures associated with the god Jupiter in Roman mythology, and his Greek counterpart Zeus, following a naming tradition that continues for newly discovered moons. The ability to observe the Galilean moons proved immediately useful for practical purposes beyond pure astronomy. Galileo recognized that the regular, predictable motions of the moons could serve as a kind of clock visible from anywhere on Earth. By carefully timing when the moons passed behind Jupiter or emerged from its shadow, sailors might determine their longitude at sea. While this method proved too difficult for practical navigation, it became important for map-making and for establishing precise time standards. One particularly important application of the Galilean moons came in 1676, when the Danish astronomer Ole Romer used them to make the first measurement of the speed of light. Romer noticed that the timing of moon eclipses by Jupiter varied depending on whether Earth was approaching Jupiter in its orbit or moving away. He correctly deduced that this variation occurred because light took different amounts of time to travel the changing distance between planets. His estimate of light's speed was within about 25% of the correct value, a remarkable achievement given the technology of the time. Throughout the 17th and 18th centuries, astronomers continued to observe the Galilean moons, refining measurements of their orbital periods and predicting their positions with increasing accuracy. The moons became testbeds for gravitational theory, their movements helping to confirm and refine Newton's laws of motion and gravitation. Laplace's work on the orbital resonance between Io, Europa, and Ganymede demonstrated the mathematical predictability of celestial mechanics. The 4 moons, visible through any modest telescope, became familiar companions to anyone who turned a telescope toward Jupiter. The 5th moon of Jupiter, Amalthea, was not discovered until 1892, when the American astronomer Edward Emerson Barnard spotted it visually using the 36-inch refractor at Lick Observatory. Amalthea was the last moon in the solar system to be discovered through direct visual observation rather than photography. Its proximity to Jupiter made it extremely difficult to see, hidden in the glare of the much brighter planet. Barnard's discovery demonstrated that even after centuries of observation, Jupiter still held secrets waiting to be found. The early 20th century brought photographic techniques that allowed astronomers to detect fainter objects than visual observation could reveal. Between 1904 and 1974, 8 more moons were discovered through careful examination of photographic plates taken of the Jupiter region. These moons were all irregular satellites in the outer reaches of Jupiter's gravitational domain, too small and distant to have been detected earlier. Each discovery added to the complexity of Jupiter's system, though the objects remained mere points of light without resolved features. The space age transformed our understanding of Jupiter's moons from dots of light into detailed worlds with their own personalities. The Pioneer 10 spacecraft flew past Jupiter in December 1973, returning the first close-up images from the Jovian system. Pioneer 11 followed in December 1974, passing even closer and returning better images. These missions confirmed the intense radiation environment around Jupiter and revealed the first hints of the diverse surfaces waiting to be explored on the Galilean moons. The true revolution came with the twin Voyager spacecraft, which flew through the Jupiter system in March and July of 1979. Voyager 1 discovered 3 previously unknown inner moons: Thebe, Metis, and Adrastea, too small to have been spotted from Earth. More dramatically, Voyager images revealed Io's active volcanoes, Europa's fractured ice, Ganymede's grooved terrain, and Callisto's ancient craters. These were no longer abstract points of light, but complex worlds with geology, history, and mysteries calling out for explanation. The discovery of volcanic activity on Io happened almost by chance, when a Voyager navigation engineer named Linda Morabito was processing an image of Io's limb to check the spacecraft's position. She noticed an unusual curved shape extending from the edge of the moon and realized she was looking at a volcanic plume rising 300 kilometers above the surface. This single observation proved that bodies in the outer solar system could be geologically active, powered by mechanisms other than radioactive decay. The discovery helped inspire the search for other active worlds throughout the outer solar system. Since Voyager, additional moons have been discovered at an accelerating pace as telescope technology has improved and systematic surveys have become more thorough. The count grew from 16 moons in 1979 to 95 by 2023, with most additions being small, irregular satellites. Many of these discoveries came from surveys using large ground-based telescopes equipped with sensitive electronic detectors. Each new moon adds another piece to the puzzle of Jupiter's gravitational influence and capture history. The next great leap in understanding Jupiter's moons came from an orbiter that would spend years in the Jupiter system rather than flying past in days. Galileo's arrival in 1995 began a new era of exploration that would reveal oceans beneath ice and transform these moons into priority targets in the search for habitable environments beyond Earth. The spacecraft named Galileo arrived at Jupiter in December of 1995 after a journey of 6 years from Earth, becoming the first mission to orbit the giant planet. Unlike the Pioneer and Voyager spacecraft that had flown past in days, Galileo would remain in the Jupiter system for nearly 8 years, making repeated close approaches to each of the major moons. This long residence allowed detailed mapping of surface features, extended study of magnetospheric interactions, and the collection of data that would reshape our understanding of these worlds. The mission also deployed a probe that plunged into Jupiter's atmosphere, returning data until crushed by increasing pressure. Galileo's arrival was nearly compromised by a failure of its main antenna, a large umbrella-shaped dish meant to transmit data back to Earth at high rates. The antenna never fully opened, leaving only a smaller backup antenna that transmitted data roughly 1,000 times more slowly than planned. Engineers on Earth developed new data compression techniques to squeeze as much science as possible through this limited channel. Despite this handicap, Galileo returned extraordinary discoveries that justified the mission many times over. The confirmation of a subsurface ocean on Europa ranks among Galileo's most significant findings, transforming our understanding of where liquid water might exist in the solar system. The spacecraft detected the induced magnetic field signature that could only come from a layer of conducting material, almost certainly salty water beneath the ice. Multiple close flybys allowed detailed mapping of Europa's surface features, revealing the chaos terrain and fracture patterns that told of a dynamic ice shell. These observations placed Europa near the top of targets for future exploration in the search for habitable environments. Galileo's observations of Io revealed a world even more active than Voyager had suggested, with volcanoes that had changed dramatically in the years between missions. The spacecraft witnessed active eruptions, tracked lava flows across the surface, and measured temperatures that exceeded any previously recorded on a planetary body. Data from Galileo helped scientists understand the connection between tidal heating and volcanic activity in unprecedented detail. The mission also revealed that Io possesses an iron core and partially molten mantle, making it more planet-like internally than its small size might suggest. The giant moon Ganymede received particular attention from Galileo, which confirmed the moon's internally generated magnetic field through multiple close approaches. No other moon in the solar system possesses such a field, making Ganymede unique among satellites. Galileo's measurements suggested that Ganymede may also harbor a subsurface ocean, adding another potentially habitable environment to the outer solar system. The grooved terrain that Voyager had glimpsed was mapped in detail, revealing a complex tectonic history that scientists are still working to understand. Even ancient Callisto provided surprises, as Galileo detected the signature of a possible subsurface ocean on this seemingly inactive world. This finding was unexpected, as Callisto's lack of geological activity suggested it might be frozen solid throughout. The presence of an ocean on Callisto implies either more internal heat than expected or antifreeze compounds that keep water liquid at lower temperatures. The outer Galilean moons proved to be more similar to Europa than previously assumed, all potentially harboring liquid water beneath their icy surfaces. Galileo's extended mission allowed the spacecraft to observe seasonal changes and ongoing geological activity that a brief flyby would miss. The mission was extended 3 times beyond its original 2-year plan, with the spacecraft remaining operational until 2003. During these extensions, Galileo made particularly close approaches to Io and Europa, gathering high-resolution data despite the increasing challenges of operating aging equipment. The mission finally ended when Galileo was deliberately crashed into Jupiter, ensuring it could never accidentally contaminate Europa with Earth microbes. Following Galileo, the next spacecraft to explore Jupiter was Juno, which entered orbit around the giant planet in July 2016, after a 5-year journey from Earth. Juno's primary mission focuses on Jupiter itself, rather than its moons, studying the planet's atmosphere, interior structure, and magnetic field in unprecedented detail. However, Juno has also made close approaches to several moons, returning new images and data that complement Galileo's findings. In June 2022, Juno flew past Ganymede at a distance of only 1,038 kilometers, the closest approach to this moon since Galileo's final flyby in 2000. Juno's observations have provided new perspectives on the moons while confirming and extending Galileo's discoveries. Images of Io from Juno show volcanic activity continuing much as it did decades earlier, with some vents persistent and others newly active. Europa appeared in Juno images with ice ridge details visible that enhance our understanding of surface processes. Though Juno's primary instruments were designed for Jupiter rather than moon observations, the spacecraft has proven valuable for Jovian satellite science. The radiation environment around Jupiter poses severe challenges for spacecraft operations, damaging electronics and degrading solar panels over time. Galileo survived in this environment far longer than its designers had hoped, a testament to careful engineering and operational planning. Juno carries specially designed radiation shielding and follows an unusual orbit that minimizes time spent in the most intense radiation zones. Future missions will need similar protections to survive extended operations in the Jupiter system. Ground-based observation of Jupiter's moons has continued alongside spacecraft exploration, with improving technology revealing details invisible to earlier generations of astronomers. Large telescopes equipped with adaptive optics can now resolve features on the Galilean moons from Earth, tracking changes in volcanic activity on Io and searching for plumes on Europa. Occultation observations, when moons pass in front of stars, reveal details about thin atmospheres and surface shapes. These observations complement spacecraft data and help plan future missions. The discoveries made by Galileo and Juno transformed Jupiter's moons from astronomical curiosities into priority targets for solar system exploration. The possibility that Europa, Ganymede, or even Callisto might harbor environments suitable for life has motivated new missions specifically designed to investigate these worlds. 2 such missions are now on their way to Jupiter, carrying instruments far more capable than anything that has observed these moons before. The next chapter in exploring Jupiter's family of worlds has already begun. 2 spacecraft are currently traveling toward Jupiter, carrying instruments designed to answer questions raised by decades of observation. Europa Clipper, launched by NASA in October 2024, will arrive at Jupiter in 2030 and begin a systematic study of Europa's ice shell and ocean. JUICE, the Jupiter Icy Moons Explorer, launched by the European Space Agency in April 2023, will reach Jupiter in 2031 and eventually become the first spacecraft to orbit a moon other than our own. Together, these missions represent the most ambitious exploration of the outer solar system ever attempted. Europa Clipper will not orbit Europa directly, as the intense radiation near that moon would quickly damage the spacecraft's electronics. Instead, Clipper will follow an orbit around Jupiter that takes it past Europa repeatedly. Approximately 50 close flybys planned over the course of the mission. Each flyby will last only a few hours as the spacecraft dips down, collects data, and retreats to safer distances to transmit its findings back to Earth. This approach allows extended study of Europa while managing the radiation exposure that destroyed previous missions faster. The instruments aboard Europa Clipper include an ice-penetrating radar capable of seeing tens of kilometers through Europa's frozen shell. This radar may detect the boundary between ice and ocean, revealing the thickness of the shell and potentially identifying pockets of liquid water closer to the surface. Understanding the ice shell structure is essential for future missions that might attempt to reach the ocean below. The radar will map subsurface features across large portions of Europa's surface, building a 3-dimensional picture of what lies beneath. Cameras and spectrometers on Europa Clipper will study the surface in unprecedented detail, identifying the composition of materials that have risen from the ocean below. The reddish-brown materials in Europa's fractures may contain salts, organic compounds, or other substances that reveal ocean chemistry. By analyzing these surface deposits, scientists hope to learn about conditions in the ocean without actually sampling it directly. The mission will also search for ongoing geological activity, including possible water vapor plumes that might allow direct sampling. JUICE will take a different approach, spending years studying all 3 icy Galilean moons before eventually entering orbit around Ganymede. The spacecraft will make close flybys of Europa and Callisto, while using these encounters to adjust its orbit around Jupiter. Eventually, JUICE will transition to orbiting Ganymede itself, becoming the first spacecraft to orbit any moon in the outer solar system. This extended orbital mission will allow detailed study of Ganymede's magnetic field, its subsurface ocean, and its complex surface geology. The scientific instruments on JUICE include a radar sounder similar to Europa clippers, designed to probe beneath the icy surfaces of all 3 moons it will study. Cameras, spectrometers, and particle detectors will characterize each world's surface, thin atmosphere, and interaction with Jupiter's magnetosphere. The mission's long duration at Ganymede will allow monitoring of changes over time, something brief flybys cannot provide. By the time JUICE completes its mission in the late 2030s, we will understand Ganymede better than any moon except our own. The questions these missions aim to answer touch on some of the most fundamental issues in planetary science and astrobiology. Is Europa's ocean habitable by any reasonable definition, with energy sources and chemical nutrients available for potential life? How thick is the ice shell, and are there pathways through which ocean material reaches the surface and surface material reaches the ocean? What makes Ganymede unique among moons, with its magnetic field and possible layered ocean? Does even ancient Callisto harbor liquid water in its deep interior? And if so, what does this tell us about the prevalence of ocean worlds? Beyond these 2 missions already in flight, concepts for future exploration continue to develop in space agencies around the world. A Europa lander has been studied extensively, a mission that would place instruments directly on the ice to search for biosignatures in surface materials. Such a mission would face extreme technical challenges, from surviving the landing on an icy surface to operating in Europa's intense radiation environment. The rewards of successfully placing a laboratory on Europa's ice, however, would justify extraordinary effort. Even more ambitious concepts involve penetrating Europa's ice shell to sample or explore the ocean below. Various proposals have suggested melting through the ice with heated probes, drilling mechanically, or using some combination of techniques. The ice shell may be 10 to 30 kilometers thick, a formidable barrier, but not necessarily impassable with sufficient technology and patience. Such a mission lies decades in the future, but the discoveries from Clipper and JUICE will help determine whether it should be attempted. The exploration of Jupiter's moons represents one thread in a broader story of discovering ocean worlds throughout the solar system and beyond. Saturn's moon Enceladus shows active water geysers erupting from its south pole, spraying ocean material directly into space, where it can be sampled. Neptune's large moon Triton shows signs of past or present geological activity that may involve subsurface liquid. Even some dwarf planets in the outer solar system may harbor internal oceans, kept liquid by their own modest heat sources. The search for life beyond Earth has shifted in recent decades from the dry surfaces of Mars and the clouds of Venus to the subsurface oceans of icy moons. These hidden seas offer environments that might be stable for billions of years, protected from radiation by kilometers of ice, potentially warmed by tidal heating or radioactive decay. The combination of liquid water, energy sources, and chemical nutrients represents the basic requirements for life as we understand it. Whether life actually exists in any of these environments remains unknown, but the possibility drives exploration forward. Jupiter's family of 95 moons stretches from the volcanic fury of Io to the ancient quiet of Callisto, from tiny Adrastea racing through Jupiter's ring to distant calm taking years to complete a single orbit. Each moon tells part of a larger story about how this system formed and evolved over billions of years, capturing visitors from throughout the solar system. while maintaining its own ancient residence. The Galilean moons Galileo discovered 4 centuries ago have become worlds in their own right, places with oceans, volcanism, and mysteries waiting to be solved. As Earth turns beneath the night sky and Jupiter traces its slow path among the stars, the moons continue their ancient dance around the giant planet. Io's volcanoes erupt silently into the vacuum. Europa's ice shell cracks and heals. Ganymede maintains its unique magnetic bubble, and Callisto preserves its 4-billion-year-old surface. Spacecraft from Earth drift through this system now, carrying instruments built by human hands, powered by our curiosity about what exists in the cold darkness far from the sun. The exploration continues, patient and persistent, following the same impulse that first turned telescopes toward Jupiter more than 400 years ago. The giant planet and its many companions orbit onward, indifferent to observation, but open to anyone who chooses to look and wonder. Night after night, orbit after orbit, the moons trace their paths, as they have since before humans existed, and will continue long after we are gone. Our spacecraft bring us images and data, transforming distant points of light into places we can know and understand. This knowledge accumulates slowly, mission by mission, discovery by discovery, building our understanding of a corner of the solar system where fire and ice coexist around a giant world.